So in this video, we're going to look at rational functions, and I'm kind of going to make this a quick rational functions one-stop shop. I'm going to link all the videos individually, but I'm going to give you examples here. So we're going to look at different characteristics of rational functions that you may see on the exam. So we have two forms of rational functions. You can see them over here on this side. We have expanded form and we have factored form. Expanded form is when the function is actually multiplied out, and factored form is when we have it in its factored form. There's multiple ways to have factored form, and I'll show you some examples on the next slide. But right now, we're just going to look at these two. Now, remember, a rational function is called a rational function because it comes from the word ratio, meaning fraction. So basically what you have is you have a fraction of polynomials. That's what a rational function is. So we're going to look at the different aspects of rational functions and compare them using this example. So I'm going to put a little box around this, and we're going to come over and we're going to look at a couple of different features. So the first one is the whole. When we look for holes in rational functions, a hole is a place in the graph where the graph just kind of jumps over a point. It's not a wall, it's not an asymptote, it's just a hole. It is a single point that does not exist on the function itself. It does not exist in those values. It's undefined for a certain value. Now, we can't see holes with the naked eye when you look at a graph. They're very, very small because we're talking about if there's a hole at 3, that means at 3.0000000000001, there is a point. So there's no way you can see something that small. So how do you find a hole? Okay, a hole, again, is a single point, and it's undefined on the graph. Okay. Now, the way you find a hole is you need to factor, and you need to factor both the numerator and the denominator, and then you need to see if there are any common factors. You need to look for a common factor, meaning that it's on the top and the bottom of the fraction, which I should say numerator and denominator, but I'm trying to keep it simple. So let's look at our example right here. For the holes, we need factored form. So I've got r of x equals x minus 4 times x plus 1 over x plus 2 times x plus 1. So when I look at this, I'm looking for a factor that is common between the top and the bottom. And I do have one. If you'll notice, x plus 1 is present in both the numerator and the denominator. What that means is wherever that factor, that x plus 1, is equal to 0, is where I have a hole on the graph. So x plus 1 is equal to 0, which means x has to equal negative 1. So my hole is at the point negative 1 for x. Now, if I wanted to actually find the y value for this, so this is my x coordinate, I would take that negative 1 and I would substitute it back into the equation. And you haven't been required to do this since we're just beginning rationals and doing the basics. But what you would do is you would go back into the equation and you would plug in negative 1 everywhere you saw an x. And if I do this, what's going to happen? Well, I see that this is going to be negative 5 up top, but what's a negative 1 plus negative 1 going to be? That's going to give me a 0. And then I'm going to have the same problem on the bottom. So you see, there's an undefined value when x is negative 1. There is no y value there. It is a hole. That is the problem. So that is why we will indicate negative 1, or x equals negative 1, as the location of that hole. I don't have a y value, and I'll put a little x in there. It is undefined. This right here makes it undefined. So that's what a hole is. Any questions? Great, y'all can't ask me questions anyway. So we're going to move along. And the next thing we're going to look at is we're going to look at vertical asymptotes. And I'm going to change the color here just because we can. So we're going to look at vertical asymptotes. I just chose my color. There we go. Okay. So we're going to look at vertical asymptotes. Now, for vertical asymptotes, we have to look at the holes first, because if we don't look at the holes first, you're going to get confused. And you're going to say, oh, wait a minute, I got vertical asymptotes there. Vertical asymptotes cannot be determined until you determine if there are holes, and you'll see what I mean here in just a second. So I've got R of x equals x minus 4. This is another one where we're going to use factored form, times x plus 1 over x plus 2 times x plus 1. Okay. Now, vertical asymptotes, I'll put the little, you set the denominator equal to 0. Okay. So you're going to set the denominator equal to 0. Now, by setting the denominator equal to 0, I run into the problem. Look what happened over here. I can't use holes. Anything that is a hole cannot be anything else. So I'm literally going to set this equal to 0, but I'm not even going to consider this because I've already identified that as a hole. So the only thing I have to set equal to 0 is x plus 2. So since x plus 2 equals 0, x equals negative 2 is a vertical asymptote that I have. So there's a hole at negative 1, excuse me, and there is a vertical asymptote at negative 2. Okay. So this is the first two, and I'm going to show you all of these on the graph. So let's go into horizontal asymptotes. So I'm going to take another one. Let me remember my function here. In fact, what I'll do is I'll copy this slide. That would probably be the best thing to do. I'm going to take that slide and I'm going to copy it. There we go. Okay. So now I'm going to keep the same thing and I'm going to go into horizontal asymptotes because we have vertical and we have horizontal. And in just a second here, when I get through all of these, I'm going to show you what the graph looks like and how we determine all these. Okay. Just trying to keep this consistent for you. All right. So here we go. Let me put my little lines back over here. Using the wrong color yellow. That's okay. All right. So now we're going to look at horizontal asymptotes. Now, horizontal asymptotes, you don't use factored form. You have to use the expanded form. Okay. So I've got horizontal asymptotes. And I'm going to use the expanded form. So I'm going to use this form here. So there are rules for horizontal asymptotes. Now we're going to do this example, and then I'm going to give you a couple of examples on the side. But here's my function. Okay. When you do horizontal asymptotes, you're going to compare the degrees of the top and the bottom. And I say top and bottom, I should say numerator and denominator. That's what I should do. So here are your conditions. I'm going to go ahead and write the conditions over here. Possible situations. Number 1, the top degree is smaller than the bottom. And if I do this properly, that basically means the degree of the numerator is less than the degree of the denominator. Okay? Here's an example. That would be something like this. R of x equals 3x plus 2 over 2x squared plus x plus 1. If I look at the degrees of these, this is degree 1, that's degree 2. 1 is less than 2. So the top is less than the bottom. What this means is our horizontal asymptote, and I'm going to put HA, is y equals 0. That's the x-axis. Oops, sorry that that's doing that. That's the x-axis. Okay, that's condition 1. All right. Condition number 2 is that the top is equal to the bottom. So basically, the degree of the numerator is equal to the degree of the denominator. So that is this example right here that we're working through. If I look at the degrees, and I look at the degree of the top, it's 2. The degree of the bottom is also 2. 2 is equal to 2. When the degree of the top is equal to the degree of the bottom, you are going to use the lead coefficients. And what I mean by using the lead coefficients is you look back up here and you look at the coefficients that are in front of your lead terms. This is an easy one because what are our lead coefficients? What's in front? Well, if you look at what's in front, it's actually 1 over 1. That's actually fairly simple. It's not always going to be that way. So 1 divided by 1 equals 1. So that means our horizontal asymptote is at y equals 1. What if I gave you another example? And I'll do another example here. Let's do example 3, and I'm going to come over here. Let's do example 3. And for example 3, let's look at this situation. So what if I had r of x equals 4x squared minus 2x plus 1 over 3x squared plus 5x minus 7. Let's just say that, okay? Well, once again, what I'm going to do is I'm going to compare the degree of the top to the degree of the bottom. Those are both equal, which means it's my lead coefficients. Well, look at my lead coefficients here. 4 over 3 this time. So what that means is my asymptote, my horizontal one here, is actually at y equals 4 over 3. So what you see on this slide is how you do the horizontal asymptotes. And on the previous slide is how we did the holes and the vertical asymptotes. So now we're going to look at the intercepts. I'm not going to get into oblique asymptotes because that's not going to be on the exam. But if the top degree is greater than the bottom degree, you have to do polynomial long division, which is not going to be on the exam. Well, polynomial long division will be on the exam, but not in the context of rational functions. So let's look one more aspect, and this aspect is actually going to be, and let me get this here, this aspect is actually going to be the intercepts. So here's my function again, and it's drawing weird things. I don't know where that came from. That's interesting. So r of x is equal to x squared. Let's see, we had minus 3x minus 4 on the top. I don't know what's going on with my program. And then on the bottom, we had x squared plus 3x plus 2. You guys can see this thing's getting a little possessed. So let's say I want to find intercepts. Well, there's 2 ways to find the intercepts. I'm going to go ahead and give you factored form as well. I apologize. I don't know what's going on with my notes program right now, but it is duplicating numbers. So I have r of x equals, I'm sure something weird is going to pop up again, x minus 4 times x plus 1. You can see it's just being a fool. And so I have these two. Now, when I find my intercepts, I'm going to try to make it through this. Let's look, first of all, at the x-intercept. Now, we've talked about intercepts. The x-intercepts, I don't know what's going on. The x-intercepts are the places where the graph crosses the x-axis. We talked about that in a previous video. This is where y is equal to 0. Now remember, when you have a rational function, dare I write this again, and here it goes again, messing up. When you have a rational function, and I'm going to use factored form for this. This is the easiest thing to do. When you have a rational function, you can set the r of x equal to y. I apologize again. I don't know what's going on. It's late. It's actually about 11:30 at night, and I'm still up at school. So my notes program doesn't want to cooperate. So r of x, this right here is essentially y. Okay, we know we can call that y. So if I want to find the x-intercepts where it crosses the x-axis, I'm going to set this equal to 0. I'm just the top. I'm going to set only the top equal to 0. I want to know where is this going to turn into 0. So I'm going to take the top and set it equal to 0. However, what did I find on the previous slide? I've got a hole at -1, right? A hole cannot be anything else. So since a hole cannot be anything else, that means I don't deal with this one. I've already established these two guys are tied into being holes. That's where there's a hole. So I can't use that. So all I'm going to do is I'm going to use the x minus 4. So I'm going to check where x minus 4 is equal to 0. And that ends up being x equals to 4. So that is where our x-intercept is. Now the way you write that as an ordered pair is 4, 0. The x-coordinate's 4, the y-coordinate is 0. Simple enough. So now let's do the y-intercept. So I'm going to do the y-intercept. We did the x-intercept. Now I want to do the y-intercept. I'm going to come over here because of room. The y-intercept is where it crosses the y-axis. And remember, the y-intercept is where x is equal to 0. So all you're going to do for the y-intercept is you're going to plug 0 in for x. Now I'm going to give you a shortcut. If you have it in expanded form, the x-intercept is just going to be this. Sorry, the y-intercept is just that, because if I plugged in 0 for all of these, what happens to those guys? They go away, right? And I'm left with -4 over +2, and -4 over +2 is -2. So that means that y equals -2 is my y-intercept, which is the point 0, -2. Now that's how you can do it in expanded form. Well, if it's in factored form, I'm going to come up here and I'm going to plug zeros in. Okay? And so on top, I get x minus 4. So on the top, I would have -4 times 0 plus 1, which is 1, over 0 plus 2, which is 2, times 0 plus 1, which is 1. So I get the same result. -4 over 2 equals -2. So you can see this is how we graph these rational functions, and these are their characteristics. Now let's go back. Okay, so we're going to add a graph. And for that graph, I'm going to add the equation, the function that I just had. So we had x minus 4 times x plus 1 And I'm going to put an extra set of parentheses around that to indicate that all of that goes on the top, because the calculator is only as smart as what we put into it, right? So, and then on the bottom, I had x minus 2, I believe, or sorry, x plus 2. We had x plus 2 times x plus 1. Now, you can see the graph. And so let's look at some of the characteristics that we found on the graph. I'm going to toggle back and forth. Let's go back to the hole. We said we had a hole at -1. So if I go back to the graph, what that means is that I literally have a hole right here at -1. Now what that means is somewhere along the line, if I were to move, whoops, this is not my night. If I keep moving this, you can see that the function itself goes past -1, but what it's saying is right there where the graph is at -1, there is a little hole there. You can't see it, but there's a hole there. That's what it means by -1. Now, we came up with a couple of other things. Let me move this back down. And I'm actually going to zoom out a little bit. So give me window zoom. And we're going to zoom out a bit. Okay. All right. So we're done zooming. Oh my goodness. This is what happens when it's this late. So we're done with the zoom. And what you can see here is I told you we had the hole at 1. So basically there's a little hole right there at 1. We also said that we had vertical and horizontal asymptotes, right? And our horizontal asymptote, remember that was the lead coefficient, that was at 1/1. Well, if you look here, if I draw this line that goes through y equals 1, that's my horizontal asymptote. That's my horizontal wall that's y equals 1. That's my horizontal asymptote that it will never reach. Now, we also had a vertical asymptote. I'll change colors here. So we had a vertical asymptote at -2. So if you look at -2, that is my vertical asymptote, and that is at x equals -2. So I've got a hole here at x equals -1. That's a hole. I have a horizontal asymptote at y equals 1 and a vertical at x equals -2. And you can see how those asymptotes work. They're walls that the function approaches, but it will never touch. Now, when we solved for the intercepts, remember, when x is 0, which means we're on the y-axis, my y-intercept was -2. So remember, we said that your y-intercept was at 0, -2. There it is. That's your y-intercept. We also found the x-intercept. And the x-intercept was 4. That's the x-intercept. And that was x equals 4. Now, how did we find these again? Let's review using the equation. I have a repeated factor here. That's the hole. Okay, that's the hole. I've got x plus 1 repeats. My vertical asymptote is whatever else after we look for holes is left over in the denominator. So my vertical asymptote, I took x plus 2 and I set it equal to 0, and that gave me x equals -2. That's how I got my vertical asymptote. That's this one. Okay? And I'll call that the VA. the vertical asymptote, okay? The horizontal asymptote was what we got by comparing the degrees. So if I were to take this and multiply it out, on top I would have, remember, x squared minus 3x minus 4 on the top. And on the bottom, I would have x squared plus 3x plus 2. So to get the horizontal asymptotes, remember I compared the degree on the top to the degree on the bottom. Since the degree on the top was the same, we took the leading coefficients, which was 1 and 1. So 1 divided by 1 is 1. That is how we got our horizontal asymptote right there. To get my x-intercept is where y was equal to 0. So my x-intercept was where the top was equal to 0. But once again, I can't use this because it's already a hole. So I could only use this. So x minus 4 had to equal 0, which was x equal 4. That is your x-intercept. That's this guy right here, okay? And then for my y-intercept, and it's a lot of writing, for my y-intercept, what I had to do was plug in 0 for x. If I plugged in zeros for all of these x's, I'm only left with these two guys. So that's negative 4 over 2, which is negative 2, and that is my y-intercept. Now, I could have also come down here and plugged in 0 for all the x's if I wanted to, and found my y-intercept that way. So here I've got an example for you actually on the graph, and I just went through everything again. So this is going to be your composite for rational functions. So hopefully this helps you with holes, horizontal asymptotes, vertical asymptotes, x-intercepts, and y-intercepts.